Okay, so in regards to our unit exam coming up here next week. So first thing we talked about in this unit, Newton's first law, okay, which we could sum up in one word as inertia. Okay. Now, is there any math to do with Newton's first law? Is there going to be any problem solving to do with Newton's first law?
Yes.
No. Because what's happening in Newton's first law? Nothing. Yeah, an object is either traveling at a constant velocity or not traveling at all. Okay? It is what happens when there is no net force present. Okay? So there's really nothing to calculate because of that. Right? We just have to understand Newton's first law and know that that's the case. When there is no net force, Newton's first law applies, and we're looking at basically no changes. Okay? How much inertia something has is a factor of its mass. Okay, so the greater the mass of something, the greater its tendency to continue doing what it was already doing, that is traveling at a constant velocity or staying put. Okay. All right, then we talked about Newton's second law. This is by far the most important and mark-intensive part of this unit and thus the unit exam. So when it comes right down to it, every single Newton's second law situation we dealt with involved two things. F net equals m times a, and F net is the vector sum of all forces. Okay, so that's Newton's second law, like really quickly summarized. Did we deal with a lot of different situations in which Newton's second law applies?
Yeah.
Yes. Okay, so there are many, many, many of them on your unit exam, okay, that you will have to figure out, okay, or deal with. Now, that said, I have not put anything novel on your unit exam. Okay, so every question to do with Newton's second law that is on your unit exam is something we have done at least once, but probably more like 3 times in class. Okay, so just be aware of that. Looking over the questions we've done in class, your Newton assignment, things like that, those would be good because that's exactly the same kind of stuff that's going to be on your unit exam to do with Newton's second law. All right, now, what is this?
Inclined plane.
It's an inclined plane. It's my favorite kind of Newton's second law problem. I really, really like that. So the reason I really, really like them is because they allow me to test a number of things about Newton's second law. There's some vector stuff in there. There's m times a, there's sum of all forces. Okay, I can even work friction into one of those if I want to. Okay, they're kind of one of those does it all type of problems, so expect to see one, okay, for sure. Okay, we'll talk a little bit more about the other ones. Obviously, we did systems. What's the trick with systems?
The acceleration is the same for the whole thing.
The acceleration is the same for all parts, at least the magnitude of the acceleration is the same for all parts. Okay, the vector could be different. So pulley systems, what we did in our lab, okay, is a prime example of that. Those things, so keep that in mind. Possibly you could get a system question, especially related to Newton's third law. Because basically all of the Newton's third law problems that we did were system questions involving more than one mass. Okay? Because, well, in a Newton's third law problem, you have to have more than one mass because every action has an equal and opposite reaction. Okay? So expect that you're going to see a 2-box problem. Okay, it's related to Newton's third law on your unit exam. Now, with the Newton's third law stuff, when it came right down to it, all the math was really what?
Easy.
Okay, yes, but it was actually all from Newton's second law. Okay, the only thing in a Newton's third law problem that's important for Newton's third law is if I can't calculate the force they want directly, I calculate its pair, okay, the other part of the pair, with another mass. And it's all, that's all sum of all forces, you know, m times a, all of that kind of stuff, because sometimes I can't actually solve for the force they want, so I solve for the one that's equal but opposite to it, and that's all Newton's second law. Okay, so the math of Newton's third law is all the Newton's second law, and then I just go, right, that one was forward, so the one I want is backwards. Okay, something like that. That's usually what happened in the ones that we did. Right, so remember that Newton's third law doesn't have any math of its own. Okay, you're really still doing m times a and the vector sum of all forces for any Newton's third law problem. Okay. Then we went on to work energy theorem, which is what we kind of just finished up here the other day. And we know that with work energy theorem, work is a change in mechanical energy. Okay. Newton's second law and work energy theorem are probably the two most important concepts in high school physics, possibly in all classical mechanics. Okay. They dictate why things move, how they move, okay, all of that. So understand that those two things are probably the two most heavily weighted things on your unit exam. Okay. Okay, law of conservation of energy. I realize we haven't done that yet, okay, but that's going to be Monday, Tuesday. And the good news, or bad news, it's going to depend on you, okay? The good news, in my mind, is that this isn't new, and I'm not teaching you anything new about it from what you learned in Science 10. The law of conservation of energy is the law of conservation of energy. It doesn't get any harder or easier, okay, than what you already know. Okay, so if you remember like the roller coaster questions from Science 10, okay, where the initial energy and the final energy are equal, okay, because in a law of conservation of energy question, no work is being done, so there's no change in energy. You just set the two mechanical energies equal and start manipulating and solve. All right, so when we do one of those on Monday, you're going to look at it and go, oh yeah, I remember that. Okay? The algebra is very similar to work energy theorem, but that's all it really comes down to is it's just algebra. Okay? If you understand that the energy at point A and the energy at point A are equal, it's just a matter of moving things around. Yeah. Okay, and the very last thing in this unit is power, and we are going to cover that on Tuesday, and it will take us a grand total of about 15 minutes. Okay, because it's incredibly simple, and I test it on the unit exam with 2 multiple choice questions. Okay, like it's a very minor part, and all power is the rate at which work is done. Okay, so something is more powerful if it can do work faster. So think about it kind of like this. If you go to cut your lawn and you have a really long lawn, okay, and a really big lawn, and you have a small, like 1/2 horsepower electric lawnmower, and you have a 4.5 horsepower gas lawnmower. I'm not saying electric is bad here, I'm just saying one's more powerful than the other, okay? Which one's going to cut your grass faster? The gas motor, because it's 4.5 horsepower versus half horsepower, okay? They'll both cut your lawn, but you're gonna be walking behind the electric one like this, because that's as fast as you can go before it'll bog out and quit, okay? Whereas that 4.5 horsepower one, you should be able to cut your lawn, well, 9 times faster, okay? Because it's more powerful, it can spin that blade better, okay? And it'll cut quicker. They both can do the job. Okay? And in fact, it's the same amount of work to cut your lawn, whichever one you use, but the more powerful one can do it faster. That's it. That's all you have to know about power. What did that take me? 3 minutes? Okay? That's all you have to know. Now, what's power measured in? Watts. Okay? We always say horsepower, but that's the imperial units. Okay? Power is measured in watts. A watt is a joule per second, because it's work divided by time. Okay, so a joule per second is a watt. Okay, that's why light bulbs are measured in watts. A 60-watt light bulb uses 60 joules of energy every second. It's why we replace them with 13-watt LED bulbs, or 6-watt LED bulbs. Okay, because, well, that uses way less energy, but emits the same amount of light. Okay, making sense? Okay, that's what's going to be on the test. Those 6 concepts, and only those 6 concepts. There's nothing else there. All right, so details about your test. There are 15 multiple choice questions. And 6 written. And some of the written, 3 of them, have a part A and a part B. All right, so in the multiple choice, things like Newton's first law, Newton's second law, work and energy, Newton's second law, work and energy, work and energy, Newton's second law, Newton's third law, Newton's second law, Newton's second law, work and energy. Am I sounding like a broken record? Yeah, kind of like I had one like Newton's third law thing in there. Newton's first law. There we go. There's something different. Energy, conservation of energy, power. There's only one power question. Okay, and for the written response, Newton's second law, heavily related to your friction lab and the force of friction. Newton's third law. Newton's second law and friction, and it's like one from your assignment. My favorite kind is Newton's second law question. Work energy theorem. And law of conservation of energy with a part B to do with work energy theorem. What 2 things do you suppose you should really study?
Newton's second law.
And
Work
energy theorem. Yeah, okay. Yeah. All right, questions from you guys? Anything you would like me to review in more detail?
How Could we do some of the work energy theorem questions?
Okay. There's a work energy theorem question. All right, so you have a 6 kilogram mass. It is being pushed up the frictionless ramp by 15.96 newtons worth of applied force. It starts at 2 meters per second at the bottom and finishes at 5.5 meters per second at the top. Calculate the final height. The ramp's 16 meters long. I will tell you that this question is far more involved than any of the work energy theorem questions on your exam. So if this one is like making sense and you're having no problem with it, then I don't think you'll struggle much with the ones I put on that list. So, in order to get this thing to go up the ramp, this is the applied force that we have to exert, okay, in order to make it go. So that's the force that's going to be doing work. Okay, everyone all right with that? Okay, that force has to not only change the kinetic energy, because we see that happening, which means there's definitely a net force here, okay, but it also has to change the potential energy. Now I'm looking at that force. It's not very big. Okay? It's not a huge force at all. We know this ramp is 16 meters long. I would imagine the angle is probably pretty low. Okay? And that my final height is also probably not very high, okay? Given the length of the ramp and how much the kinetic energy changes. All right, so what I need to do is, as we always do, set up work energy theorem. Okay? So I'm just going to delete this down here. Don't need that yet. All right, and I'm going to say that work is a change in mechanical energy. All right, that's going to mean that applied force they gave me times the distance, the length of the ramp, is going to be equal to the change in mechanical energy. So that's going to mean my final potential plus my final kinetic minus my initial potential plus my initial kinetic. Now, before I go any further, are any of those zero? Which one, Kat?
Initial?
Yeah. My initial potential energy. That's zero, because where am I starting?
On the ground.
Like at the bottom of the ramp, where my height would be zero. So that's gone. I can eliminate that right now. Okay? What I'm looking for is part of this term. Right? Final height would be part of my final potential energy. So can I move this over here right now? Yeah. Okay, so I'm going to say my work minus my initial kinetic energy equals my final potential energy. Whoop, no, not minus, plus, sorry, because it's there, plus. All right, what I'm looking for is part of EPF. So what do I need to do with EKF? Subtract it over the other side. Okay. Oh, geez, they're still doing all my work here. All right, so I'm going to bring that over. So I'm going to have force applied times distance plus my initial kinetic minus my final kinetic equals my final potential. Now I can expand that out again and say, all right, force applied times distance plus 1/2 mvf squared, or sorry, mvi squared, minus 1/2 mvf squared, so just plugging in the formulas for our energies there, equals, okay, my final potential, which would be m times g times h final. All right, I want h final by itself, so what do I do with the m and the g? Divide. Okay, now I just got to plug in my numbers. All right, so I'm going to have 15.96 times 16. So that's the work that's being done. All right, I'm going to add that to the kinetic energy we had at the beginning. So 1/2 times 6 times, it was 2, right, squared? Yeah, 2 meters per second, okay? And then I'm going to subtract the 1/2 times 6 times, whoops, I've got that backwards. No, I don't, okay. Times, what was the speed at the top? 5.5. 5.5? Okay, and then I'm going to divide that by 6 times 9.81. All right, 15.96 times 16 plus 0.5 times 6 times 4 minus 0.5 times 6.
You put in a plus. Instead of a minus.
Oh, instead of a minus. Good eye. Minus 0.5 times 6 times 5.5 squared equals divided by 6 times 9.81. Look at that. 3 meters. Okay, so the final height of this is 3 meters. Now, as I said, on the test, I'm probably not going to give you one that's that involved. Okay, they're going to be more like only one kind of energy is changing kind of questions. So in this one, both potential and kinetic change. Okay, in the ones on the test, it's only one kind of energy. And for the one that's a part B of the conservation of energy question, okay, it's like taking a number you calculate with the conservation of energy question and then using it in a work energy theorem calculation. So it's nothing this involved. It's like a single calculation, right? And there's a bit of an, like a written part, so where you're going to explain work energy theorem and how it applies to the situation in the work energy theorem question that's by itself. Okay, so it's like an A and a B, but the part B is an explanation. You've got to tell me why. Okay, you do this, you do these calculations, and you tell me why. Okay, everybody with me there? All right, so you do have to not only be able to do the math, but you got to understand and be able to explain how work energy theorem works. Okay, what else?
Newton's second law.
What kind?
Inclined plane.
Okay. All right. This one is probably a tiny bit harder than the one I put on the test because it involves the coefficient of friction, and I'm pretty sure I didn't put coefficient of friction in the one on your test. Okay. So you got a 20 kilogram box, and it is placed on this 25-degree incline. There's a coefficient of friction of 0.137. Calculate the acceleration of the box. There are no other forces, so no one's trying to push it up or down. Okay, so on this one, right, we've got F parallel acting down the plane, which we haven't calculated yet, so that'll be our kind of first few steps here. We got to calculate FG, which will be 196.2. Right, and then we'll have F normal over here, which we will also have to calculate, and F parallel, which we have to calculate. So we got 25 degrees here, okay, and we got to go about calculating Fn, which will be the cos of 25 times 196.2. Right, so that's 177.81. Right, and then we got to calculate F parallel. So that'll be the sine of 25 times 196.2. And that's 82.92 newtons. All right, so now that we've got those things, okay, now we can start heading towards getting all the stuff we need. So this is going to be 82.92. Okay, I got to calculate the force of friction. So that'll be mu times the normal force. Okay, and that was 0.137. So 0.137 times our normal force. We're looking at 24.36 newtons. Now what? I've got all my forces, now what? Find F net, vector sum of all forces. All right, so F net then is going to be 82.92 minus 24.36. All right, 58.56 newtons, and then I divide that by the mass, and I've got my acceleration 2.9. We only have 2 sig digs there. 2.9 meters per second squared. Downhill, down the ramp. Okay, something indicating which direction it is going. Yep. All right, questions on that one? Okay. 2-box question?
Yes.
Okay. All right, so box A is being pushed by an applied force that causes both boxes to accelerate at 1.3 meters per second squared. Right, so that's important. A force of friction of 8.5 newtons acts against the movement of box B. What is the force of box B on box A? Which box should I use? B. Yeah, I got to use box B. I know more about it. All right, so I'm just going to isolate box B. Okay, so here's box B, 9 kilograms. This is the force that A exerts on B, and this is the force of friction that they gave me, 8.5 newtons. All right, what's the importance of the force of A on B? What will it help me get? Nope. If box A pushes on box B, what does box B do? Pushes back. Is that the force I'm looking for? Okay, so is the force of A on B equal but opposite to the force they want me to find? Yes, okay, that's the Newton's third law part of that question. Once I recognize that, the rest of this question is a Newton's second law question. Isolating box B. It has 2 forces acting on it, and I know its mass and acceleration. Okay, so that's the only Newton's third law part of this question. It's all intuitive. I just have to look at the relationships and say, all right, they want me to find this force, but I can't, so I'll find its action-reaction pair. Now I can move toward finding that force. All right, so first thing I want to do is find F net. Okay, so that's going to mean that I'm going to take the mass and the acceleration, so 9 times 1.3. That will give me the net force acting on box B. Okay, so it's 11.7 newtons. All right, so F net equals 11.7 newtons, which equals the force of A on B plus the force of friction. So I want to find the force of A on B, so I'm going to subtract the force of friction. So I'll have 11.7, which is forward, minus negative 8.5, because friction is resisting, will equal the force of A on B. Okay, so I'll have 11.7 plus 8.5. Okay, so the force A exerts on B is 20.2 newtons forwards. So what is the force B exerts on A? 20 newtons backwards. We only have 2 significant digits. Okay, so the math of it, all Newton's second law, and a pretty basic question with 1 mass and 2 forces. Okay, it's the intuitive part that's challenging, figuring out what force I can get that gets me what I need. Okay, the question on your exam is very similar to that. Okay. All right, I posted this morning a review package, or actually I haven't posted, I've been waiting for this to get recorded, and then I will attach it to that and it'll be posted, so you'll have a review package. The review package has 7 dynamics questions on the first page, right? So there's not much to it. There's, they're old exam questions. They're very much like what's going to be on your exam. Okay? So I would suggest doing them. There's a key, okay, for them, so you'll know if you did them right. And then the page after that has some work energy theorem questions. Some of them are similar to what we've done, and some of them are way harder than anything I would ever ask you. Answers are also on there if you want to challenge yourself with those. Okay? Your best bet for preparing for the exams to go over the questions we've already done and the 7 that I put on that test, or on that review package, sorry. Okay? Because like I said, there's nothing on the test you haven't done before many times. Okay? All right, any other ones?
Do you have a static cable tension?
No.
Okay.
I don't have a problem about that. There could be multiple choice related
Yeah,
to Newton's
okay.
second law about a static situation, but I don't have a static problem. Yeah. That's a system question. And we already did that one. Oh, that's a good one. That's a good one. We got a few minutes left. You can give that one a try. Maybe we'll go over the answer to it on Monday if you remind me. Okay, I realize that probably nobody's done this one, but okay, the trick on this one that people miss is that, yes, there's a force of gravity acting down here, but your normal force and gravity are not equal because there's a vertical component to that pulling force that is taking some of the weight away. All right, so you can calculate that, subtract it from Fg to get your correct normal force, which you would then use here to get your force of friction. Okay? What? All right, so just that's the trick to that one. We had one just like that on your assignment. Okay, maybe there's one like that on your test. So yeah. All right, so study hard over the weekend, guys. And if you have questions next week, you can come see me at nighttime or after school, before school.